Hi there, so I'm at the top of that ski lift. I've literally just got off and it's just started to snow. It's the first time in a week actually. I've just recorded some information using Geotracker, which is basically the altitude change and speed of the lift and so on. So we're going to use that information to do some basic calculations when I get home, and obviously not on top of a mountain. So that we can work out the average power required to pull all the people and the chairlifts up that massive distance. I suspect it's going to be pretty huge. Anyway, I'll just spin around, give you a bit of a view up the mountain and just over the far side there. It's pretty damn stunning, I've got to say. Right, I'm going to head off down the mountain now, so I'll catch up with you later.
So hi there, you can see the screenshot of the Geotracker output for the duration of the ski lift. So there's quite a bit of information here. Some of it's a little bit contradictory. It says altitude difference 166 meters and vertical ascent is 180 meters. I'm not sure why there's a discrepancy, but I'm basically going to say that H is equal to 180 meters. I'm going to use the ascent value. And then if you look at the speed chart, here we can see that there's a consistent speed. So it's saying that it's 10 mph, 10 miles per hour. So there's the mixing of units. So a little bit inconvenient, but I'm going to do a conversion. So speed or velocity of the ski lift, which is consistent, it's constant. The ski lift didn't stop, which kind of made a change, and kind of lucky. So we can use that consistency quite nicely. So I know 10 miles an hour is 16 kilometers an hour, which is 1600 meters in 1 hour. And if I divide through by 3600, i.e. 60 squared, that gives me meters per second. So that actually rounds to 40 over 9, which is approximately equal to 4.4 recurring meters per second. So there's our second piece of information. We can also look at the time index on the speed time graph. So and the elevation chart the same. We've got 5 minutes and 20 seconds. So we do 5 times 60 plus our 20. So our time is 320 seconds. Okay, so we've got 3 valuable pieces of information here. We've got the ascent or the height. We've got the velocity, which is 4.4 meters per second, and we've also got the time of ascent. Now, the purpose of this investigation is actually to work out the power generated by the motors. So the power is effectively how much energy is required to move all the lifts, and we'll call that M, the mass of all the lifts and all the chairlifts on the lift, GH, and we're also going to divide that by T. So we have the value of H, which is the ascent height. We have the value of T. It's actually the value of M we're missing, which is the mass of all the chairlifts and all the people. Now that might seem very difficult to judge, but I've come up with a solution to that. So I'm going to use the mass of one chairlift, which I'm going to call M subscript C for chairlift, and we multiply that by N, which is the number of chairlifts. Okay, now I did a little bit of research, and the mass of one chairlift for the 4-person chairlift is 200 kilograms. So we got 6-person ski lifts that I was on for this particular ascent. So I scaled it up, and I made an estimate of about 300 kilograms. So we can work out, we know what that is, and if we know what N is, the number of chairlifts, we can actually work out M. Now, I wasn't going to sit at the bottom and count them because they go round and round, and I'd probably count them more than once, and it was quite boring. So I've actually come up with another solution. I did a little video just coming up, which showed the timing between the subsequent chairlifts, and therefore we can use the speed, which you've got up there, the velocity, 4.4 meters per second, to work out the distance between them, and we know the distance of the distance we travelled, so we can actually work out the number of ski lifts there are. So I can actually work out what N is. So I'll go ahead and do that now.
some little dudes going down the slope outside our apartment from the balcony. Anyway, so there's the chairlift going up from where I'm about to ski down to, which is a chairlift called Colossus. The purpose of this video is to time the intervals between the chairlifts going past the main upright. So that way I can work out from the average speed of the chairlifts how far apart they are, and therefore how many there are in total on the chairlift. So it's a necessary part of my calculation. I hope that makes sense.
So, a quick reminder of what we know. We know the time of the lift descent. We know the altitude increase, which is 180 meters, not 80 meters. We know the velocity is about 4.4 meters per second, and we know the mass of one chairlift unloaded, so with no people on it, is about 300 kilograms. So we need to know how many chairlifts there are. So we know the time for the chairlift was 7.5 seconds. So we know that the velocity or the speed is 4.4 meters per second. So we know that the chairlifts are a certain distance apart. Okay, so we know that 7.5 times 4.4 is the distance between chairlifts. Okay, so 4.4 times 7.5, I'm just rounding here, is about 33 meters. Okay, so that's the distance between each chairlift. And the total distance we know is going to be equal to 320 multiplied by the speed, 4.4 meters per second, which is approximately equal to, so I do 4.4 times 320, and we get about 1,400 meters. Okay, so the number of chairlifts, and we called that n, was going to be approximately equal to 1,400 divided by 33. It's not going to be a nice number, but I'll just get a rough idea. 1,400 divided by 33. So I make approximately 42 chairlifts. Okay, now that's going to actually allow us to work out the mass, total mass, we just called that m, is going to be about 42 multiplied by 300, and that's just the chairlifts themselves. Okay, so if I times that by 300, we're going to get approximately an impressive 12.7 tons, which is about, we'll do it just rounded. It's actually 12.727, but of course we're estimating here. So we're talking about 12,700 kilograms roughly. We've also got to make an estimate of the mass of the people. So to do that, we're going to call that MP. On this particular day, it was quite quiet. I sort of noted there was about 2 people per chairlift, so they certainly weren't full. And if we say each person's about 60 kilograms, so each chairlift is about 2 times 60. I mean, there are 42 of them. Okay, so we're going to do 2 times 60 times 42, which we got to about 5,000 kilograms. So it's certainly significant. Okay, so in total, our mass of all of our chairlifts and people, and that's actually not even very loaded, is going to be 12,700 plus 5,000 is going to be about 17,700 kilograms. Okay, so that is our ballpark figure for what is being hoisted from the bottom to the top of the slope. So that's a huge amount of mass. Okay, so here we have a cross-section of the chairlifts, or the whole chairlift going up. There's only 5 of them on here, so obviously that's just a small proportion of the entire chairlift, but we'll just use that as an example or a demonstration. So you can see that there are 5 lots of W acting downwards, but all in different positions. Now, we could consider every one of those chairlifts moving up through a gravitational potential energy change of mgh, and each h being different. But there's no need. We can greatly simplify that because the distances between each of the ski lifts is uniform. We can basically assume that we can actually compress all the ski lifts, all the chairlifts, into one mass So in this case it'd be 5W, or for a number of lifts n, which we're yet to determine, it'll be n multiplied by W. And the centre of mass of all the chairlifts will be actually halfway between the starting and the end point of the chairlift, so basically half the altitude change. Okay, so that's going to greatly simplify our calculations. So here we are on the very last part of the calculation. So obviously we've established that the height or altitude change h is actually no longer 180 meters, because we're considering the entire mass to be centralized at the halfway point. So we actually now have a revised value of h to be 90 meters. Okay, so the potential energy gained by all the masses, 17,700 roughly. As I said, it's a very kind of liberal ballpark figure, but we'll go 1,800 kilograms. Sorry, 18,000 kilograms, should I say? And we're going to multiply that by g. We call that 10. Multiply that by h, which is obviously 90, and divide the whole thing by the time period. So that's the potential energy change divided by the time, and that will give us the power. Okay, so obviously energy required to move all of the masses up the slope, or halfway up the slope in this case. That will give us the power, which is exactly what the number we're after. So one final few button presses on the calculator: 18,000, make sure I get enough zeros, times 10 times 90. And obviously while we're doing this, please bear in mind that this is a very, very lower limit. We're talking about 50,000 or thereabouts, again slightly rounded, 50,000 watts or 50 kilowatts. Okay, now I definitely believe that that's a very much a lower limit, because of course the motors themselves are nowhere near 100% efficient. There's the mass of the cable we haven't even considered, but it gives you some idea about the power that's required for these things, which is pretty impressive. Okay, so I hope that kind of all made sense to you, and thanks for watching.